So picture a traditional rocket launch in your mind for a second. You were probably visualizing like millions of pounds of steel
Oh, yeah.
and that deafening roar that literally shakes the ground beneath your feet.
Exactly.
And obviously a towering inferno of fire just slowly, painfully lifting this massive vehicle off the pad. It's an awe-inspiring display of brute force, right?
Absolutely. It's an explosive event.
But what if we could erase all of that? Like, no roaring combustion, no massive metal fuel tanks, no fire at all.
It sounds like science fiction.
It does. But just imagine a silent, totally invisible beam of light shooting up from the surface of the ocean and quietly lifting a perfectly smooth drone straight into orbit.
Welcome to the deep dive. You handed us a pretty massive stack of leaked architectural blueprints, financial risk assessments, and these highly confidential technical notes, all dated July 7th, 2026.
Yeah, that stack was quite a read. I bet. So our mission today is to decode them for you. We are going to unpack this incredibly revolutionary system known as Project Phaeton. We really want to find out exactly how this beamed energy propulsion system plans to drag humanity out of the heavy, explosive chemical age of rockets and basically launch us directly into what the engineers in these documents are calling the Photonic Age of solid-state, electricity-driven orbital delivery.
Yeah, and we really, really need to emphasize the sheer scale of the ambition in the documents you provided. Like Project Phaeton is not pitching an iterative improvement.
Right.
They're not talking about slightly more efficient rocket fuel or, like lighter landing legs. Their stated goal in these blueprints is to render the entire $500 billion chemical rocket industry completely obsolete.
Just gone.
Overnight. Yeah, they are plotting to drop the cost of a launch down to the literal price of industrial electricity. And they plan to take the payload efficiency of a spacecraft from a rather dismal 4% up to an astonishing 84%.
Okay, let's unpack this because to really understand why an 84% payload efficiency is such a massive revolutionary leap, we first have to talk about the fundamental underlying flaw of legacy aerospace.
Right, the core problem.
Yeah, so think about flying a traditional chemical rocket like trying to deliver a single pizza in a massive semi-truck.
That's a great way to look at it.
Right, but here is the catch. 96% of that semi-truck's weight is just the highly explosive gasoline tank required to drive it down the street.
Exactly.
When we launch chemical rockets, we are essentially strapping our precious cargo and, our astronauts to a giant controlled bomb on the launch pad.
Right. And to take your semi-truck pizza analogy a step further, imagine if we just took the engine and the gas tank out of the truck entirely.
Just left them behind.
Yeah, just left them back at the pizzeria. That is the Phaeton solution in a nutshell. In aerospace, this semi-truck problem is known as the tyranny of the rocket equation.
Right, the rocket equation.
Yeah, if you want to go further or faster, you need more fuel. But fuel is incredibly heavy.
Yeah.
So to carry that extra fuel, you have to add even more fuel just to lift the fuel you just added.
Right. It's a vicious, inescapable cycle of diminishing returns.
Exactly. So Phaeton's radical paradigm shift is that they are simply offloading the energy source. The vehicle no longer carries its own fire,
Wow.
and it no longer carries thousands of tons of propellant. The drone itself, at least according to the schematics here, is completely passive.
That's wild.
It is an ultra-lightweight monolith made of 100% graphene-aerogel.
Yeah, I'm looking at these diagrams of the aerogel frame right now, and there are literally no fuel tanks. There are no combustion chambers.
Nothing like that.
I get that the energy is offloaded to the ground, but how does the energy actually bridge the gap to the drone?
So that is the job of the Helios Beam. The blueprints detail this ground-based power plant featuring a 10-gigawatt array made up of 10,000 synchronized fiber lasers.
Okay, but wait, my brain is kind of snagging on the physics here. Because a laser is just concentrated light.
Right, so yes.
So if you shine a massive flashlight up into the sky, no matter how incredibly bright it is, it doesn't part the clouds.
Right, of course not.
How does shining a giant laser at a drone actually help it cut through the friction of the Earth's atmosphere?
Well, it relies on a very specific atmospheric mechanism called laser filamentation.
Laser filamentation.
Right. So the Helios beam doesn't just shine a continuous unbroken beam of light. Instead, it emits ultra-short femtosecond pulses.
Femtosecond.
Yeah, we're talking about bursts of energy that last a quadrillionth of a second.
Oh my God.
I know. When these insanely powerful rapid-fire pulses hit the atmosphere, They trigger a self-focusing effect within the air molecules themselves.
Okay.
The energy is so intense that it essentially drills a plasma filament through the air.
It drills a hole?
Essentially, yeah.
Yeah.
This rapid heating and expansion creates a temporary low-pressure vacuum tunnel right through the sky, directly in front of the ascending drone. So the drone isn't pushing through thick air.
It is slipping through a frictionless tunnel.
Exactly.
Okay, so the laser acts like a high-tech snowplow, just clearing a frictionless vacuum path. But clearing the path isn't enough, right? I am staring at these propulsion notes, and without any fuel to burn and expel out the back, my brain literally cannot compute how this thing actually generates forward thrust. Like you said, there are 0 moving parts.
You're completely right to be puzzled because it's completely counterintuitive to how we've achieved flight for the last century.
Right.
And that brings us to the Magnetohydrodynamic, or MHD, propulsion architecture.
MHD.
Yeah. So as the Helios beam is drilling that vacuum tunnel, it is simultaneously performing a second crucial job. It is ionizing the ambient air that gets trapped inside the drone.
Inside the drone.
Yes, because the drone's graphene-aerogel frame isn't a solid block. It is highly porous, like a rigid sponge.
Oh, I see.
So the laser hits that trapped regular air and turns it into an electrically charged plasma.
Okay, let me see if I'm tracking this. It's somewhat like a magnetic railgun, or, one of those high-speed maglev trains you see in Japan.
Yes, very similar principle.
But instead of using magnetic tracks to accelerate a solid metal train car forward, this system is doing the reverse. It is using the sky itself as the track. Like, it grabs that newly created electrically charged plasma and magnetically accelerates it backward through the spongy frame of the drone.
That is the exact mechanism. It operates on a principle of physics called the Lorentz Force.
The Lorentz Force.
Right. And the most brilliant part of this design is how they achieve it through solid-state integration. Like, there are no heavy mechanical motors to break down.
No moving parts.
Exactly. And no fuel pumps to freeze. Instead, they utilize what are called Hallback magnet arrays.
Yeah, the notes mention these arrays are located in Zone C of the drone. But what makes a Hallback array different from just a regular magnet?
So think of a standard refrigerator magnet. It sticks to your fridge on one side, but the back side of it doesn't really attract anything.
Right.
A Hallback array takes that concept and magnifies it to an extreme engineering degree. The engineers specifically arrange a sequence of permanent magnets so that their magnetic fields effectively cancel each other out on the outside of the array.
Oh, wow.
But they combine and compound their strength on the inside. These rings are 3D printed directly into the carbon frame using high-conductivity graphene tracks.
That's incredibly clever.
It really is.
Yeah.
And when you run an electrical current through the plasma inside those highly focused magnetic rings, it creates a massive Lorentz force. It literally violently shoots the plasma out the back of the drone at exhaust velocities exceeding 20,000 meters per second.
And the performance specs they're projecting from that are just wild. I mean, the math here says it achieves a specific impulse of 3,200 seconds.
Yeah, that number is staggering.
So, right. To put that into perspective, for anyone familiar with rocket engines, that is over 3 times better than the absolute top-tier hydrogen-oxygen combustion rockets we use today.
And because the entire system is solid-state and electronic, the maneuverability completely outclasses physical rockets.
How so?
Well, the blueprints detail a solid-state vectoring system. Because they are steering with pure electromagnetism, they can manipulate the thrust electronically to handle atmospheric turbulence with microsecond response times.
So no steering fins.
Right. There are no heavy, fail-prone mechanical flaps or gimbals. According to the Monte Carlo simulations provided in the risk assessments, this electronic vectoring achieves a 97.8% launch stability success rate.
Okay, that sounds flawless on paper, but I have to push back on this design a bit. We're talking about pointing a 10-gigawatt laser at a vehicle.
Yes, we are.
That is an absolutely insane, city-powering amount of raw energy. I don't care how fancy the carbon frame is. Wouldn't blasting a featherlight aerogel drone with a 10-gigawatt laser instantly vaporize the drone into a cloud of ash the absolute second the beam makes contact?
What's fascinating here is how the materials science engineers approached that exact hurdle, because they didn't try to build a thicker, heavier shield to block the laser.
Okay.
Instead, they used advanced chemistry to let the laser
Through it.
Yeah. They doped the drone's energy coupling core, which the schematics label as Zone B, with a compound called Hexagonal Boron Nitride, or HBN.
Doping meaning they, like, infuse the carbon with it. How does that stop the burning?
Exactly.
Yeah.
So by infusing the core with HPN, they fundamentally shift the material's optical absorption window. Think about it like a sheet of colored glass or a one-way mirror.
Okay.
If you shine a specific wavelength of light at a properly tipped piece of glass, the light passes straight through without heating up the glass itself.
Oh, I see.
The HBN doping creates what they call optical transparency for the precise frequency of the Helios laser. This allows for what they term volumetric energy absorption. The laser energy passes harmlessly through the outer hull of the drone to ignite the trapped air inside, rather than causing surface ablation on the outside.
So it doesn't vaporize the hull because the hull acts like a window, just letting the light pass right through to the internal channels.
Precisely.
Okay, I buy that. But what about the friction of the atmosphere itself? Even if it is flying up a low-pressure vacuum tunnel, the specs say this drone hits Mach 25 in under 120 seconds.
Right, and that is where the ablative nosecone in Zone A comes into play.
Ah, okay.
While the core lets the laser through, the nosecone has to bash through whatever residual atmosphere remains at hypersonic speeds. The nosecone is doped with Silicon Carbide, or CC, which acts as a high-emissivity thermal shield.
So it takes the brunt of the heat.
Exactly. It is specifically designed to protect the drone against the 3,000 degrees Celsius friction of Mach 5 plus atmospheric entry. And furthermore, the 3D printing of the monolith uses a functionally graded density.
Meaning the structure isn't uniform.
Right, exactly. The carbon lattice is printed denser in the load-bearing areas and more porous in others.
That makes sense.
This highly specific architecture allows the entire frame to uniformly absorb and survive the crushing force of 100 Gs of acceleration.
And the documents make it clear this isn't just theoretical math they are kicking around in a boardroom somewhere.
No, not at all.
The sources state this structural resilience is actively being physically validated. Like, they are currently using the LMAT-1 testbed and a subscale prototype they call Phaeton 0 to prove that this 3D printed hull can consistently take the laser impact and the G-forces without sublimating into dust. And it's currently boasting a 99.4% structural survival rate.
Which is incredible. The structural success is highly promising for launching heavy, inanimate cargo. But if we look at the operations manual, things take a very dark turn when we examine the blueprints for the human-rated mode.
Here's where it gets really interesting. 100 Gs of acceleration is totally fine for delivering satellites or raw materials. But if you put a human passenger in a 100 G ascent, they would be instantly crushed.
Without a doubt.
The blueprints introduce a solution called a liquid immersion pod. It is designed to mitigate that extreme trauma, bringing the internal passenger load down to a 15 G ascent.
Still heavy, but survivable.
Right. It's essentially a high-tech shock absorber where the astronaut is suspended in fluid to keep the human body intact under the crushing weight of the acceleration.
It is a conceptually viable protection mechanism, but the risk assessments reveal a pretty sobering reality regarding the human risk gap.
Yeah.
Because while the drone's structural survival rate is an excellent 99.4%, the human survivability rate drops significantly to just 91.4%.
A nearly 10% failure rate for human passengers. Yeah. That is entirely unacceptable. You can't put astronauts on a system where 1 in 10 dies. What is causing that massive drop in safety compared to the cargo runs?
The core issue outlined in the risk assessment is the phase synchronization hazard.
Phase synchronization.
Yeah, it all comes down to a process called coherent beam combining, or CBC. Remember, the Helios beam isn't just one massive single light bulb, right?
Right.
It is an array of 10,000 individual fiber lasers that have to perfectly sync up.
Right. They have to act as a single beam.
And not just generally point in the same direction. They have to combine their phases to maintain a single, incredibly precise 1 centimeter focal point on a moving target that is 10 miles away in the sky.
That sounds impossible.
Think about it like trying to get 10,000 different people to stand in a stadium and shine individual handheld laser pointers at the exact same millimeter on a coin.
Oh, wow.
And that coin is flying through the air 10 miles away at Mach 5.
If even a handful of those people let their hands shake, the combined focal point wavers and the power drops.
Exactly. If that synchronization wavers for even a fraction of a second, the energy delivery to the drone fluctuates. And if the energy fluctuates, the MHD thrust stutters.
Oh, I see.
During a 15G ascent, those rapid, violent G-force fluctuations would cause catastrophic trauma. It would be instantly lethal to anyone inside the immersion pod. The liquid can cushion a steady 15G push, but it cannot cushion rapid, stuttering impacts.
So the drone itself survives the bumpy ride, but the human suspended in the fluid inside does not.
Right.
That perfectly explains the urgency behind the 2026 ground tests at the Dallas facility, because the notes explicitly state that bridging this risk gap is their absolute primary challenge. They're going to use a 1-megawatt pilot beam to track the Phaeton Zero prototype, and their stated success metric is to try and achieve 95% beam coherence at the exact moment of target impact. They basically have to prove they can hold those 10,000 laser pointers perfectly steady on the coin.
Right, and if they can't master coherent beam combining, Phaeton remains a cargo-only vehicle forever. But, assuming they do master the laser synchronization, and they solve the human suit problem.
Right, human suit problem.
The question becomes, how does this actually operate in the real world? Because firing a 10-gigawatt laser requires a staggering amount of power infrastructure.
Which brings us out to the ocean and the introduction of the climbing barge. This entirely changes the physical footprint of space launches.
Oh, totally. The climbing platform is an engineering marvel in its own right. It is an offshore barge that acts as the dedicated power plant for the Helios Beam.
Right.
Instead of relying on a municipal grid, it harvests renewable energy directly from ocean waves and vast offshore solar arrays. It then stores all that gathered energy in massive graphene-aerogel supercapacitors.
Which means the entire launch process is entirely carbon neutral. We are completely replacing the 500-ton CO2 footprint of a traditional chemical rocket launch with harvested ocean and solar power.
It represents a total green transition for orbital logistics. And from a business perspective, the documents refer to this as the Space FedEx model.
Right. Because if you aren't blowing up massive metal rockets and you aren't burning millions of dollars in chemical fuel, you aren't burning cash. Which actually brings me to a pretty significant mathematical discrepancy I found in their pitch deck regarding those finances.
Oh.
Yeah. The documents proudly state a $112 billion net present value, or NPV, for the project. But if you actually run the numbers based on their projected 10-year net profit of $135.4 billion, and you apply their stated 12% discount rate, the true NPV is actually $57.2 billion.
Well, yeah. It is a fairly common, albeit aggressive, forecasting tactic in venture capital pitch decks. They will often under-discount future cash flows to inflate the perceived current value for investors.
Definitely an investor illusion.
Yeah.
But here's the crazy part. Even with that math fixed and the true NPV effectively cut in half, the profit margins they're projecting are still absolutely staggering. By years 6 through 10 of operation, they're projecting 85% profit margins.
And those margins are entirely possible because of the unprecedented drop in the cost of a launch. Let's break down the comparison for you. A highly efficient legacy chemical rocket, like a Falcon 9, costs roughly $2,500 per kilogram to get to orbit.
Right.
That equates to about $25 million per launch. The Phaeton architecture drops that cost to just $15 per kilogram.
$15. I could send a 100-kilogram satellite into orbit for less than the cost of a used car.
You really could. Because the cost of the launch is simply the cost of the industrial electricity required to charge the capacitors on the barge.
That's insane.
The marginal cost of a single Phaeton launch is projected to be an almost unbelievable $45,000. And remember, there is no highly volatile fuel to carefully load.
Right.
The drone itself is a completely reusable solid-state block of carbon that essentially just catches light. Because of this, they project a dizzying turnaround time.
Yeah.
We are looking at a cadence of 15 to 24 orbital launches per day per barge.
So what does this all mean? We are looking at a massive leap from a high-stakes, hardware-loss combustion model where you literally throw away millions of dollars of meticulously engineered metal and chemical fuel every single time you launch, to a highly reusable electricity-driven utility service.
Exactly.
It essentially functions as a permanent space elevator, just without the physical cable connecting the Earth to orbit. It's a continuous high-speed conveyor belt into space.
If we connect this to the bigger picture, the implications extend far beyond just cheaper communication satellites or, setting up lunar supply chains.
Right.
The sources explicitly mention that this offshore barge model creates something called sovereign space access. Think about the current paradigm. Launching rockets requires massive, highly volatile chemical infrastructure, vast tracts of secure land, and immense industrial wealth.
Oh, totally.
It is a game only superpowers and massive corporations can play.
But if the barrier to space is suddenly reduced from immense industrial wealth to simply owning a coastal barge and paying for electricity, it changes everything.
Right. This raises an important question for you to think about. How will this completely rewrite the geopolitical balance of power on Earth? When every single coastal nation, regardless of their current industrial base or military budget, suddenly has a direct, dirt-cheap, high-speed pipeline to orbit, the monopoly on space access dissolves overnight.
That is a wild thought to end on. Just from a world where we rely on the explosive, deafening fury of chemical bombs on a launch pad, to a silent, invisible laser beam quietly rewriting the rules of global power from a barge out in the ocean. Thank you for coming along on this deep dive with us today. Keep questioning the blueprints of the future, and we'll catch you on the next one.